Today I will be discussing the application of Newton's second law, also known as the momentum principle, on a lacrosse ball rolling at an ideally constant velocity. The form of this equation that I will primarily use is final velocity equals initial velocity plus net force over mass times the change in time. I will discuss how I was able to use this equation to predict the velocity of my ball for a total of 1.4 seconds using Tracker and the computational model, and then I will speak about the resulting graphs. All in all, the computational model did not coincide with my recorded data for the entire time period, but it was enough to get a good estimate of what would happen if I was able to keep the ball rolling at a constant velocity for an extended period of time. I started by rolling a lacrosse ball across the floor. For this experiment, I factored out the beginning of the roll because the ball's velocity would be increasing, and also factored out most of the end since friction would make the ball's velocity decrease. As you can see on Tracker, I placed the origin of the axis at the center of mass of the ball. This meant that my ball's starting position vector would be 0, 0, 0 meters, and the x-axis was parallel to the ground. I could have easily changed the axis to be practically anything I wanted. I could have moved the origin so it would have given me a new start position and therefore moved the graph over. I could also have rotated it, as you can see now. This would make it travel across the y-axis. Also, I can flip it back. And then I could have even relabeled the x-axis, so instead of moving in a negative x direction, it was moving in a positive x direction. Either way, the move will be the same. As the ball rolled, I was able to track the change in position and time as you can see in this table to the right. I will later use this data to compare my computational model to the data that I have collected here. For the model, I'm going to assume that the net force acting on the ball is 0, since for this time, the ball is no longer accelerating, so there is no force going in the negative direction, and friction and air resistance should be so small that they are negligible. Also, gravity pushing down on the ball and the force pushing back up cancel each other out. Using VPython, I was able to create a computational model that illustrates the ball's movement based on just a couple pieces of data. Looking at the code, you can see that I included pieces of data from the experiment, including the ball's mass, which is 0.145 kilograms, beginning position, and beginning velocity, as well as the start time. I also wanted to run this code for the time my ball is rolling in the video, so it is run while time is less than 1.402 seconds. The final piece of data I needed is the net force. Since I am assuming the velocity is constant during my experiment, I am able to state that the net force is also 0, because there is a constant and equal force on the ball at that time. If the ball was speeding up or slowing down, we would know that the net force would have to be some value, positive or negative, based on the direction and size of the force. Finally, all the pieces are in place, so now the code will simply repeatedly predict the velocity based on the information it has. This is what it looks like when we run the code. As you can see, when I pull up the original of the ball, the views look almost identical. It is only when we look at the graphs that we can really see the discrepancies. As you can see, the experiment data is shown with the blue dots, while the model's prediction is in red. The predicted position decreases at a more constant rate, while the experiment position begins to curve up. In other words, the model is staying at a constant velocity, while the experiment's velocity is decreasing to a degree. Obviously, the experiment is not ideal, so the net force did not end up being 0. There could be a few causes of this, including friction or air resistance. We could have made the model more accurate had we been able to measure the forces being applied to the ball, including the push that propelled the ball. Another reason for this discrepancy could be because the ball curved as it rolled. So when I tracked the point in Tracker, they were skewed, whereas the model assumes the ball is moving in a straight line the entire time. In conclusion, the data is far from perfect. but it illustrates the physics ideas key to understanding Newton's second law. It showed how we can predict velocity.